Welcome. This problem involves a mixing tank. So methane and oxygen are mixed. The conditions are a pressure of 200 kPa absolute, a temperature of 100 degrees C. The velocity of gases entering the mixer is 5 meters per second. So this velocity and this velocity are each 5 meters per second. The density of the exiting gas here is 1.9 kilograms per cubic meter, and the goal is to find this velocity right here. So we're looking for the velocity at the exit. As usual, I'll connect this problem to what I already know. Methane is natural gas that I use in my home to heat. This natural gas is being mixed with oxygen. Oh, this could be some kind of mixing device for a heater or some other kind of combustion device. I recognize that both methane and oxygen can be modeled with the ideal gas law, and I recall that I'm going to want to use absolute temperature and absolute pressure when I do my calculations. I see mixing, 2 inflows and 1 outflow. This suggests drawing a control volume and applying the continuity equation. The continuity equation says that accumulation of mass in my control volume is the rate of mass flow in minus the rate of mass flow out. Well, I don't expect any mass to accumulate in this tank because I expect it to be steady state. So I would see that the rate of inflow via methane and oxygen is equal to the rate of outflow of the mixture. Let's go ahead and get started with the problem solution. In my documentation, I strive to capture most of my information with my system diagram. Right here, notice that I convert pressure and temperature to absolute values because this makes application of the ideal gas law easier. Steady state means that all properties of my system remain constant with time. When I did my calculations later in this problem, I came back here and wrote down the fluid property data that I needed. The goal is the mean velocity at the exit of the mixing tank. To reach my goal, I selected the continuity equation. I sketched my control volume, and I wrote the general form of the continuity equation. The amount of mass in this region inside the control volume is constant with time. So the change in mass with respect to time in the control volume would be 0. In terms of the inflows, there's the inflow of mass there and an inflow of mass there. And so I capture those two ideas there. And there's an outflow of mass in the mixture. So one term there, and I capture that idea there. And so the continuity equation reduces down to this equation. So I rewrote the equation to put the inflows on one side of the equation and the outflow on the other side of the equation, and next I applied the flow rate equation, in particular the idea that mass flow rate is equal to density, area, velocity. Let me show you a simple idea for remembering this equation. Using units helps me remember this equation. So the units of this are kilograms per cubic meter. The units of area are meters squared. And the units of velocity, so there's area, and the units of velocity are meters per second. The meters cancel, and I get kilograms per second, which are the units of this term. And I use this basic idea of remembering units to help me remember many equations in engineering. So after I've applied the flow rate equation, I have this equation right here. You can see my term-by-term analysis. The goal is right here, and I have two unknowns, this density and this density. So my new goals are the density of the methane and the density of the oxygen. And of course, to find these goals, I'm going to apply the ideal gas law. When I apply the ideal gas law and do my term-by-term analysis, I can see that I can solve for my two new goals, so my work is done. So my plan is to calculate my two density values with the ideal gas law and then calculate the mixture velocity with the continuity equation. Here's the ideal gas law applied to the oxygen. So P is equal to rho RT, so rho is equal to P over RT. Here's the equation. Substitute in numbers, units, carry and cancel as usual. And here's the value of the density of the oxygen. Similarly, I next calculate the density of the methane. Here's the result. 1.0351 kilograms per cubic meter. Lastly, I apply the continuity equation to calculate the velocity of the mixture. So I took my equation from the previous section, rewrote it, got this equation, then I substituted in numbers right here, kind of a lengthy calculation, and here's the final result. The velocity of the mixture is 6.34 meters per second. I really hope you enjoyed watching this video. Thank you very much for listening. We'll see you next time. Bye-bye.